I'm going to move to a new chapter today on sequences and series. A sequence is basically just an ordered list of terms, so you'll see I have a couple listed below. First one, 1, 5, 9, 13, 17, has 5 terms in it, and you'll see there's kind of an order of an adding of 4. In this next sequence, I have a and 3a plus 1 and 5a plus 3 with the dot 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 at the end. That dot 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 means it goes on forever, so there's an infinite number of terms. Any sequence that ends is finite. Sequence that never ends is called infinite. Now, as far as notation goes, here's another sequence, 2, 5, 8, 11, 14, all the way to this a with the subscript n. The 2 represents the first term, the 5 the second, 8 the third, etc., until I get to this last term, which we call the nth term. Notation for each term: the first term is represented by a with the subscript 1, second term a with the subscript 2, all the way down to the nth term, which is a subscript n. And different books from different publishers will use different notation for this. Ours uses the a with the subscript. Other books I've seen use t. Some books use s. If I want to generate terms in a sequence, I need a formula to do that with. And I think the easiest formula to work with is something called an explicit formula, because what an explicit formula does is it allows you to pick the term that you want in the sequence, plug its associated number in, and get that item out. For instance, if I want to find the first 3 terms and the 10th term in the sequence described by these explicit formulas down here, all I really need to do to find the first term is say, I want n to represent 1. So a sub 1 represents my first term, and then therefore every n is going to have a value of 1. So this is 2 to the first minus 1, which is going to equal 1. If I want the second term, I let my n value equal 2. Then I have 2 squared minus 1 is 3. Third term, 2 to the third minus 1 is 7. And 10th term, let n equal 10, so I have 2 to the 10th minus 1 is equal to 1023. You'll notice I have multiple values of n in this next problem. Works the same way. First term, n equals 1, therefore everywhere I see n, I plug a 1 in, and I end up with 3 halves. If I want the second term, plug a 2 in. It's 4 times 2 minus 1 over 2 times 2, or 7/4. Third term, 4 times 3 minus 1 over 2 times 3, which is 11/6. 10th term, 4 times 10 minus 1 over 2 times 10 is 39/20. Writing an explicit formula is a little more challenging than just plugging numbers in. You have to think a little bit, and for now, we're not going to have a way to necessarily cookbook it. In other words, easily generate a formula. We're going to have to think through this a little bit. So the idea behind generating an explicit formula is letting n equaling 1 in your formula, and every time you plug that 1 in, you get this term out. When n equals 2, you'll get this second term out. When n equals 3, you'll get this third term out. When n equals 4, you'll get this fourth term out. Now, as seen in our previous examples, these equations can either be 1 line, 2 lines, have fractions in them, what have you, whatever it takes to get the answer we want. And you'll notice in this case, this problem's not too bad, because if n equals 1, I get a 1, n equals 2, I get a 2, etc., and you'll notice all the numbers below are just 1 more than the number above. So if I let my explicit formula be the nth term is equivalent to n over n plus 1, that gets every single term in my list. In the second term, or the second sequence, we do the same thing. N has to equal 1, 2, 3, etc., etc. And go through a whole series of guesses, if you will. It doesn't look like there's any additive pattern here. If I multiply by 2, then that's not going to work. Let's take a look at powers. If I square 1 and square 2 and square 3 and square 4, notice every time I do that I'm one off of my number. So if I take and make my nth term equaling to the subscript squared plus 1, that'll get me every number in that set. This last one's the trickiest. You'll see that this also has some kind of power function within it because I have 1, 8, 27, 64. These are all perfect cubes. Alright? So if I were to take and go n cubed, that would almost get me there. However, first term's positive, second term's negative, third term's positive. By plugging in 1, 2, and 3, I'm not going to get that alternating power. If I were to take and say, well, what if I had a negative n cubed? Then in my first term, I get a negative 1. So that's not going to work. I need to have some way to change the multiplication of 1 and negative 1 to this. And I just kind of gave you the hint. I'm multiplying negative 1 in an alternate sequence. So rather than making this to the n power, in which my first term would be a negative, I raise negative 1 to the n plus 1 power. In so doing, I get an even power for my first term of negative 1, which makes this positive. On my second term, I get my 8 here, and 2 plus 1 is 3, negative 1 to the third power is negative, and it alternates through. This is kind of like a negative counter, if you will. And that's my own little word for that. So that's how you write some explicit formulas. Again, it's a little guess and check work, but I think you can get through it at this point. Recursive formulas are much different than explicit formulas in that they use previous terms to generate the next term in the sequence. So you'll notice here's a sequence of 2, 5, 8. There's a pattern of adding 3 to my previous term to get the next term. And in essence, that's really all we need to do. We need to add 3 to previous term. Now the way I say that in terms of a recursive formula is I say my nth term is equal to 3 plus my previous term. And the way to say your previous term using sequence notation is a with the subscript n minus 1. That right there means the previous term. So now if I want to generate my first 4 terms of the sequence, the caveat is that you're given that first term so you can generate the ones after it. So if I want my first term, which I know is 300, and I'm trying to get my second term, then this says 1/5 times my previous term. My previous term, I'll just write this out one time, is a sub n is equal to 2 minus 1 plus 10, which says the second term is equal to 1/5 times my first term, which is my previous term, plus 10, or 1/5 multiplied by 300 plus 10, which is 70. Now I'll expedite this a little bit. So this time, to get my third term, I'll make this a little bit quicker and say I've got 1/5 times my previous term, which is the second term, plus 10. And I have 1/5 of 70 plus 10, which I believe is 24. To get my fourth term, I take 1/5 my previous term, which is my third term, and add 10 to it. That gives me 1/5 times 24 plus 10, or 24 over 5 plus 50 over 5, 74 over 5, and that's my fourth term. Let's do this for a couple more sequences just to get the hang of it. I know my first term is 10. I want my second term, which is found by taking 1 over my first term. That's the previous term, which is 1/10. Get my third term, I take 1 over my previous term, which is my second term. So that's 1 over 1/10, which is equal to 10. And then my fourth term is 1 over my previous term, which is my third term, or 1/10. You'll notice in this next example, I have a previous term and a value of n in the denominator. So notice how this will work. I want to find my second term, which is my first term, over my subscript, because that's the n value of 2. So in this case, my first term was 12 over 2, which is 6. To get my third term, I'm going to take my previous term, which is my second term, over, now in this case, the n value goes to 3 because that's my subscript. So I've got 6 over 3, which is 2. To get my fourth term, I use my previous term, which is my third term, over, notice my n value is now 4. And my third term was 2 over 4 is equal to 1/2. Now we're going to move on to talk about factorials. What a factorial is it's an expression written in this form, and with, we call this a factorial, but it looks like an exclamation mark. And what it means is take that number and then decrease that number by 1 until you get all the way down to 1, and take all those numerals and multiply them together. You can see right here that 4 factorial is the same as 4 times 3 times 2 times 1, which is 24. And by definition, 0 factorial is defined to be 1. If I want to simplify 6 factorial over 3 factorial, that's not necessarily 2 factorial. It's 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, which in essence is 6 times 5 times 4, or 120. To get n minus 4 factorial over n factorial, keep in mind n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 until I get down to 1. N minus 4 factorial is going to start with the n minus 4 term. And then I take 1 from that and multiply it. So that's n minus 5. And then I take 1 from that until I get all the way down to 1. You'll notice everything from n minus 4 down to 1 is going to reduce with a like term in the denominator. So this term goes here. Let's do it in green so you can see it a little better. These are the same. These are the same. And then everything all the way until 1 is going to be the same. So those will all reduce, leaving me with an expression of 1 over n times n minus 1 times n minus 2 times n minus 3. And that's how that reduces out. When we talk sigma notation, this is a Greek letter sigma here. And in math, it means the sum of, or find the sum of. And a typical sigma notation setup is the following, which says as n goes from 1 to n of a sub n, add everything up. In other words, find the sum of this series generated by the equation of a sub n. This will typically be an explicit formula, where n begins at 1 and increments by integers of 1 until it reaches the value n. Let's go in practice because this is a little touchy-feely and out there right now. So here's a couple examples of a sigma notation sum. This says find the sum of the series that is made by n starting at 1, plugging it into the formula, incrementing by integer values of 1 until I get to 6. So let's do that. I have 5 and n starts at 1. Then I increment by 1 and say 5 and n equals 2. 5 times n equals 3. Whoops. N equals 3. 5 times n equals 4. 5, n equals 5. And 5 times n value is 6. This gets me 5 plus 10 plus 15, etc., etc. Until I get to 30. I add all that up. We got 30, 50, 80, 105. And that is the sum of that sigma notation problem. Let's do it again here. You'll notice my n value doesn't start with 1. It doesn't have to. It can start anywhere you want it to. So in this case, we start at n equals 4, and I have 2 to the 4th plus 1. I increment by 1. I have 2 to the 5th plus 1. 2 to the 6th plus 1. And 2 to the 7th plus 1. And then we have to add all those quantities up. And I end up with about 244 after I plug that into a calculator. So next we're going to express a sum using sigma notation. And you'll notice I need an explicit formula to generate this pattern right here. So I'm going to need to plug an n equals 1 in to get this number out, n equals 2 to get 6 out, n equals 3 to get 9 out, and n equals 4 to get 12 out. That's the way I choose to do it. So you'll notice this isn't too hard to generate. Our nth term is basically equal to 3n. So if I say I want to add the terms generated by the sequence of 3n as n goes from 1 to 4, incrementing by 1, that will generate that sum. Let's do it again. A little bit more difficult set of terms to generate, although really not too bad because we can see n equals 1 here, n equals 2 here, n equals 3. And you'll notice that the pattern is squared terms. So this is n equals 10. And therefore, if I want to add the sequence of 1 over n squared as n equals 1 to 10, this will generate the following sum. Let's continue. Here's another one. I want n equals 1 to generate the first set, n equals 2 to get the second, n equals 3, the third, n equals 4 to get the next. And we've done a couple of these already. You'll notice I need 2 and 3 on the top. So my nth term would be n plus 1 times n plus 2. That'll generate 2, 3, and then 3, 4, and 4, 5, and 5, 6. The bottom we've kind of seen before. If we square each term and add 1, that will generate my denominator. So I only got 4 terms. I'm going to let n equal 1 to 4 of n plus 1 times n plus 2 over n squared plus 1. And I think that's probably the easiest way to get that problem done. A couple more. This next one's a little more difficult. We haven't seen this. The top, not too bad. The denominator is going to be a little more difficult, and you'll notice we have that alternating positive and negative, so we'll have to use that power of -1 in here. N equals 1 has to get me a 4. N equals 2 gets me a 16. N equals 3 gets me a 64. N equals 4 gets me a 256. And this goes on forever. So what I'm going to have in this case is an infinite sum. I want to plug in 1 and go to infinity and get an nth term for this. So you'll notice on the top, these are powers of 4. 4 to the first, 4 to the second, 4 to the third, 4 to the fourth. So we have 4 to the n as my numerator. The denominator, 1, 2, 6, is kind of tough to see, although I can point out that this is multiplied by 2, multiplied by 3, multiplied by 4, and that, in a sense, is a factorial problem, because this is 2 times 1, 3 times 2 times 1, 4 times 3 times 2 times 1. So when you see 1, 2, 6, 24, that's basically a pattern for n factorial. So let's go ahead and do that. And now the problem I have is I need a negative on my first term. So in order to get that negative, what I'm going to do is I'm going to multiply this fraction by -1 to the n power. Because what that'll do is it'll make my first term negative. My second term is going to be squared, so it makes it positive. Third term cubed negative. Fourth term, etc., etc. Now we're going to use a calculator to find the sum of the sequence. So here we go. What I first want to do is find the summation on the calculator. If I hit math and I move to the number, I believe it's 10 in this case, notice I get summation or sigma. I'm going to hit that. Next thing I need to do is plug in my formula. Now these say n, but I'm going to use x in this case. X cubed plus x squared. And then after you've written your formula, you're going to put a comma, followed by the variable you're using in this case, or the counter. And that's going to be x. And then you're going to tell the calculator where to start. We're going to start at x equals 1 and put a comma again. And you tell the calculator where to stop. We're going to go to 10. Close your parentheses, hit enter, and it will calculate everything for you. So the answer in this case is 3,410. And that's how you use your calculator to find a sum. That's all we've got. Fill out your summary, do your My Math Lab, and we'll talk tomorrow.